So you've got other things on today as well, or one? Yeah. Right. Thought you'd stick around for the lecture as well then. Good. Well, we may as well make a start. So, as I was already outlining, under the exercises tab or menu, sub-menu on Web CMS, there's a bunch of exercises that are defined for chapter 4, in this case, of the 3rd edition of the text. I'm not sure whether it's the same chapter number in the most recent edition, but the content is going to be very similar nonetheless. And in order to avoid any confusion anyway, I put up the questions on the website as well. So that's a little bit small to read. I might just make that a bit bigger. Righto. And as for the actual exercises, that is this set. Right. Some pictures of four input lookup tables. I think we looked at that in class, this particular exercise. And the exercises are at the end of the chapter here. Right, which might be a little bit small to read, but I'll make it larger. And then, of course, all the exercises that are starred here, like this one here, 418, has a star associated with it. They have answers associated with them at the end of the text, which I've also included in this photocopy. So they're here, the chapter 4 answers. As you can see, there's no working shown, it's just the answer, so at least you can check whether you understand things or not. And this Q&A is provided as an opportunity for you to ask questions that you didn't get the right answer and you didn't understand why you didn't get the right answer, for example. In order to get the most out of these tutorials or these Q&A sessions, I would suggest that you try to answer the questions that are in the exercise set before Friday, before we meet, so that you know what you can and can't answer off the cuff, so that you're prepared and can ask a question about stuff that you don't know. All right, so that's the assumption I'm making, that you're prepared, and will ask questions about things that you don't really understand properly, be they from the lectures, the exercises, or from the laboratory work. Right, so for this week, the solutions to the exercises that I nominated, so there were a number of exercises that I thought were relevant, that are useful for preparation for the quiz, that embed the theory. The ones that are starred are the ones that I provide a solution to. Many of the non-starred ones are actually starred in the chapter and therefore have an answer at the back of the text anyway. But of course the solution isn't provided. Sorry, the working isn't provided, just the answer. So the solutions that I provide are also illustrated here. So these are the exercises that I had starred. Let me get rid of that. It's not relevant. So 4.9, 4.20, 4.37, and exercise 10 there. So these are the solutions there. So I wasn't going to go through these unless you've got particular questions about any of the solutions that I've put up. Yeah. 4.2. Okay, that's not one that I've worked a solution to. So this is, let me just bring that exercise up. That has a solution in the back. Yeah. Okay, let's just have a look at it. 4.2. So find the minimum cost SOP and POS forms for this 3-variable function. 4.20. Okay.
You did it in the solution that you gave.
Yes, I did.
But when they said simplest realization, do they mean in terms of like cost, or is it just like to remove all the unneeded variable?
Could you repeat the first part of that question?
Find the simplest realization of the function, and then they give min terms, assuming that the logic gates have a maximum fan-in of 2. When they said simplest realization,
It's minimum cost.
Oh, minimum cost.
Yeah, that's generally what that means. Sorry if I didn't make that clear in some sense. So what's the question? Is it whether that refers to minimum cost or? Right. Okay. So does the answer make sense then?
Yes.
So that was this truth table. It's this one here, where it's the sum of min terms. The function of 4 variables has min terms 0, 3, 4, 7, 9, 10, 13, 14. So we can fill those in directly from that number, those min terms that are given, right? Because we know min term 0 goes into the top left corner here. So 0, 1, 2, 3. 3 is this guy here. 4, 5, 6, 7 is that guy there. 8, 9, 10. 10 is this guy. 11, 12, 13 is this guy. 14 is down here, and 15 is the 0 that's there, right? So obviously we can group things together. Firstly, I mean, you can see that that's a checkerboard pattern again, which suggests it's going to involve exclusive OR in some way. I've just written out the simplified sum of product form here, and then recognize that I have not x1 and x1 outside of not x3, not x4, or x3, x4, which is the first term, which is exclusive NOR. And then I have x1 outside of not x3, x4, or x3, x4 bar, which is exclusive OR of x3 and x4. So effectively, it's x NOR, not x, and x NOR, and x XOR, which means that it's actually the x NOR of x1, x3, and x4, right? x1, x NOR, x3, x NOR, x4 is what you can think of this function as being. But the question was, given that you only have fan-in of 2 gates, how do you simplify this? Well, this is already in fan-in of 2 form, because no term here has more than 2 inputs. Yeah?
So in the labs, when it asks us to derive the simplest Boolean expression,
Yeah.
are we meant to just calculate SOP and POS and
Yep.
take the minimum, or
Yep.
do we have to simplify that?
Well, use the tools that you know about that are allowed for you to use. I don't think I excluded using K-maps, but you need to be able to show which one's cheapest.
After the K-map, once we do SOP and POS,
Mm-hmm.
we still have to simplify even
No. So there's no simplification possible after that. So were you on the forum? Were you asking that question on the forum? Because that question came up on the forum as well. Yeah, so no, there's no further factorization that you should be doing at that point in time. Okay? I think if you're trying to factorize as well, then you're turning it back into a very hard problem because there are many choices as to how you might factorize. So it's just not practical. Usually what you want to do is just find the minimum cost K-map realization. Any other questions on that?
So in the drawing, and then compared to your expression, because on the left, it is like the input of like not
This guy here,
yes.
well, this is just the exclusive OR of X3 and X4,
Yeah.
right?
But then after that, for the right side, you could put a NOT gate and chuck it into another AND.
Yeah, that's right. I'm ANDing the exclusive OR with X1 and ANDing the exclusive NOR with not X1. So it's effectively this part here that's on the lower branch, and it's this part here that's on the upper branch here. Is that clear? Yeah, it's a little only slightly different to this realization because we know that this expression here is the complement of this expression. So we evaluate this expression and AND it with X1 here, and then we take the complement of it and AND it with X1 bar. All right. All good? All right, are there any other questions?
Could you also show for 4.39, because I couldn't really understand.
So that's one that I don't have the solution for, is that right?
And it's also not in the back of the book.
Right, 439. Okay, here we go. Find the minimum cost circuit. So we're looking at this problem here. Can you read that at the back? Yeah, okay. Find the minimum cost circuit consisting only of two input NAND gates for the function X1, four input function with such a min-term list. Assume that the input variables are available in both uncomplemented and complemented forms. Hint, consider the complement of the function. All right, well, I don't know why it says hint, consider the complement of the function. Other than that, we'll probably have fewer terms, given it's quite a long list there. And the other thing is that if we were to implement the function as it's specified there, it would be an AND OR circuit, right? So if we want to implement the complement of it, we really want to, well, we can convert all of the ANDs to NANDs, that'll complement those. And we need to convert the OR as well, I think. I'm not 100% sure on how easy or difficult that is. So what's your question about this particular problem?
I don't quite get when it said like consisting of only two input NAND, because we can get the product of sum of product from the K-map, and then do we draw the diagram and then change it to NAND?
I don't know what the easiest approach to this is either. I haven't really thought about the problem before. There's probably a few ways of going about it. Can you read out the function for me?
The min terms are 0, 1, 0, 1, 2, 3, 4, 6, 8, 9, 12.
I'd be tempted to try and simplify it first rather than anything else. So is that the correct list? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So if we wanted to simplify the SOP, simplify it as an SOP function, we'd group those guys together, we'd group these guys together. They're both essential prime implicants. We'd group this guy with that guy, and we've grouped this guy here with these two, correct? What would that give us? So this would be x1, x2 at the top, x3, x4, the less significant variables. So we would end up with what's that top row? Not x3, not x4. The left column is right. The covering this one down here, so that min term or that term, that sum term that we want, that's going to be not x1, because in these two columns we have not x1, and in these two rows we have not x4, right? So it's not x1, not x4. Okay, so that's covered this one here. So to cover this one, we also need to have not x2, not x3, right? See, they're already all two input AND gates anyway, aren't they? So if you wanted to draw this guy, you'd have because we're assuming all of the inputs are available in complemented form anyway, x3 bar, x4 bar, x1 bar, x2 bar, x1 bar, x4 bar, x2 bar, and x3 bar, right? And they're coming into an OR gate, like so. Right, now to convert that to a NAND-only circuit, what do we need to do? We add bubbles here, and we add bubbles here, right? And essentially, this means that this becomes a 4-input NAND gate. How am I going to draw that? So rather than drawing it this way, I'm going to have a 4-input NAND gate at the back end there, right? So I have to convert this guy into 2-input NAND gates, that's all. Right?
But why is it NAND?
Oh, sorry, 2-input, yeah, 2-input NAND. I thought that's what the goal is, isn't it?
No, I meant,
Assume that, so you only have 2-input NAND gates.
but shouldn't it be connected to one 4-input OR gate?
Yes, that's what we had. And when we put the bubbles in there, to turn that into an AND, it's a NOT OR, which is an AND NOT, or a NAND. But another way of thinking, so this guy has to be turned into two input NAND gates. So I'm not too familiar on how this works either. So if we had A, B, C, D, the NAND of that is equal to not A, or not B, or not C, or not D, right? Which we can group as this way, right? Which is equal to the NAND of A and B, or the NAND of C and D. Which is equal to the NAND of but I need to double that, I think. Is that right? Because if I do that, if I complement that, then that's going to be just the NAND of A, B, C, D. So I think it might be easier to just think of it as the prior line there rather than the rest, because that's an OR. So effectively this is a two input. No, I can't draw there. I'll draw it over here. That's a two input NAND coming into an OR gate, a two input OR gate, which is effectively the same. To turn that into a NAND, I have to complement. I'm going to have to insert quite a few bubbles, right? So to turn this into a NAND, I'd have to complement that, but to keep the sense the same, I've got to put another NAND in there. So effectively, to redraw that has to become and then that goes into a two input NAND gate. Okay? So that's deriving it from first principles. I don't know how considering the complement of the function might be easier. We could try that and see whether that gives us a better solution. But do you see that to replace that 4-input NAND, I actually need to derive that circuit? Is that clear? And did you see how I got that? I got it by looking at, well, what is a 4-input NAND? That's expressed this way, as well as the OR of two 2-input NANDs. But to get the OR, I've got to basically complement and then complement again, right? And then I can convert that into a NAND. So if you were considering the complement, you'd be looking at this bit here and this bit here, certainly a few fewer terms, which would be, this is so F bar is equal to so this is x2 x4 or x1 x3, right? That's the complement of F, because that covers all of the zeros that are there in SOP form, right? Who's with me? Who's not with me? Who doesn't follow what I've just put up there? So we're just looking, we're taking the suggestion of the question, which is to consider the complement of the function, rather than looking at the function directly, which is what I did over here. So F bar, I have to cover all of the zeros and treat them as ones in order to be looking at the complement of the function, right? Because F is actually x2 bar or x4 bar and x1 bar or x3 bar, right? So it comes from F is equal to, this is the POS version, x2 bar or x4 bar and x1 bar or x3 bar. Right, so the complement of that is this. Right, so what does that look like? Well, that's a bit of a simpler sum of products form because it's got an OR gate that's only 2 inputs, and I can see now why they suggested looking at the complement of the function, because to turn that into 2-input NANDs is a lot easier, right? Just got to put a bubble here, a bubble here, a bubble here, and a bubble there, and we're done. Which is quite a different expression to what we've got up there, which is really, really bizarre. So if we went backwards, I wonder whether we could derive the same expression. Oh, so hang on, that's F bar. So that's F bar, right? So we've got to remember that this is actually F bar, not F. Oh, crikey. I think I'm going to have to revert to just using red. Oh, God. It's also not very good. I guess because I've drawn there. Or rather, rubbed out here. So it's a bit moist. So all I'm doing is drawing this circuit. We actually have to add another inverter here because this is F. Sorry, that's F bar and we want F, right? Well, you've only got 2-input NAND gates. So that's an inverter in 2-input NAND gate form, right? Okay, so that's definitely easier if you follow the hint. Are there any questions about this, what we've done?
So when you converted the over to NAND, you add an inverter at the output.
Hang on. Let me just take a photo of this. Righto, so sorry?
So on the F component, when you converted the OR gate to the NAND gate, to the NAND gate, but you added an inverter at the front instead.
Because that's F, because this part of the circuit is F bar, but I want F.
If we were to add a NOT gate, it would be the same.
What do you mean? Instead of this NAND gate, yeah, that'd be the same, have the same effect, but the spirit of the question is you only have 2-input NAND gates. So you've got to create your inverter with that as well. Right? Yeah.
More of an admin question. Do you know which of the labs have Vivado installed? Is it just
It's only Brass and Lyre at this stage. Yep. So if you're planning on coming in the weekend, I think Lyre should have it installed, but might be worth your while just dropping in there before you leave today to check. But it should be there. Any other questions? Right. So should we move on to the lecture then? All good? No other questions? Right. Let's do that then. All right, we were looking at lecture 4. These were the main objectives for this lecture, to learn about common combinational sub-circuits that are used, namely multiplexers, encoders, decoders, and code converters in general. We were also going to look at other VHDL constructs that are often used to specify combinational circuits. So we were looking at non-simple concurrent assignment statements, and I'll just quickly review those in the context of how you specify 2-to-1 mux. And today we're going to continue on with looking at sequential statements for specifying a 2-to-1 multiplexer. In reviewing the lecture, I came to realize that there's probably a slide there that might be confusing if you don't really appreciate that in circuit design there's two meanings to the word sequential, as opposed to what you're probably more familiar with, that sequential always means one thing after another, right? In circuit design, we distinguish between combinational circuits, which are just an output which is directly related to its inputs, and circuits that contain memory elements, such as flip-flops or RAM, to store data in between clock cycles. Those are known as sequential circuits in digital design, because you have a clock that's sequencing the events that are occurring, and I guess the sequential, the word sequential, that adjective, comes from that sequencing of the clock. We're not yet looking at clock-based circuits, so the sequential that we're referring to here is more about the one after another evaluation of statements within the VHDL description. We'll finish off with an exploration then of Shannon's expansion theorem, which allows us to implement any function that we like using multiplexers. Right, so just a recap of where we were. We looked at several different ways to specify 2-to-1 muxes using different non-simple concurrent assignment statements. The first one of which was this selected signal assignment, which has this syntax: with some signal select, make an assignment to a particular other signal based on what values that signal might have. So in this case, we're specifying a 2-to-1 mux, so there's only two alternatives really. When S is 0, we want to assign W0 to F, and when S is not 0, we want to assign W1 to F. Recall that in VHDL, if we're dealing with standard logic signals, those types of signals can have any one of 9 different values, not just 0 and 1. There's also don't care, uninitialized, unknown, weak, weak tending to low, weak tending to high. There's several other alternatives. So in this particular case, the way this mux were to work, according to the behavior in any case, is that only when the select signal is 0 should a W0 be assigned to F, the W0 input be assigned to F, and in all other cases, irrespective of what the signal value is, we'd be assigning W1 to it. That's not exactly the way this circuit actually looks, because this circuit is going to make sort of an assumption that S is either 0 or 1, right? We may not know it if we're analyzing it, but when it's running, S is going to have some value. It's going to be either 0 or 1, assuming the circuit has been designed properly, assuming there are no open circuits or no short circuits within our design, then S will either be high or low, and this will work perfectly well as a mux. It'll only really either route W0 through to F if S is low, and if S is high, it'll route W1 through to F. Okay? So the behavior is a little bit more general than this circuit description, or the resulting circuit in many ways. I indicated to you that if you're implementing a mux, if your design requires a mux, then this is one of the ways that you should really describe it. You shouldn't describe it at the structural level. It's not required. You can use a selected signal assignment statement like this. However, there is another way that you could describe a mux, and that's with the so-called conditional signal assignment statement, which in this case, it's even less wordy, I guess, than the previous version. Assign to F W0 when S is 0, otherwise assign W1 to F. Has the same semantic meaning. So again, we're going to get a 2-to-1 mux resulting out of this. And today, I'm going to introduce another way that you could describe a 2-to-1 mux, namely using a so-called process. Now, this is probably one of the concepts that's going to lead to a large amount of confusion within your mind as to what's actually going on, because a process is a non-trivial concept. There's many things that could be said about a concept, about a process. The first thing to note about it is that processes are typically used to describe complex behaviors. A 2-to-1 mux in many ways is arguably too simple and does not deserve a process, all right? But we're using it because it's a nice simple example to start off on explaining some of the intricacies of a process. The next thing to note about a process is that all of the statements that are within the process are evaluated sequentially by the tools. Okay, what does that mean? So we talked a little bit about this on Tuesday, and I don't think I got the message across very clearly. I'm not sure that I'll get it across clearly today either. Firstly, I want to just concentrate on what I mean by the tools here. What do you think I mean by the tools? Yes, synthesis tool, for example. You've probably come across another tool already in the labs. Yes, the simulator. So they're both tools that can understand VHDL and synthesize a netlist on the one hand, or provide a discrete event simulation given some set of inputs of the code that is being presented. So the tools will evaluate these statements sequentially that are inside the process. But the resulting circuit is going to be a parallel circuit, just like all the others. It's not going to be any different from the mux that you've seen so far. I'm only going to say this once at this stage and not really explain it any further. The process actually takes only infinitesimally small amount of time to execute. Therefore, it's concurrent with all other concurrent statements. Okay? What is important is if you have a sequence of assignments to the same output signal here, that it's only the last one that will be committed when the process is exited. Okay? Because it's a sequential set of assignments, only the last assignment that's going to count when you exit the process by ending here. Okay? It's also somewhat important to realize that this f, the output f, is only assigned a value once, really. It has a number of pending assignments to it, and it's only the last one that's committed when you exit the process. The process overall is only triggered when one of the signals in its so-called sensitivity list experiences a change of signal value. Okay, there are processes that don't have a sensitivity list, and we'll come to those, but for today we're only looking at combinational processes. So a process that describes combinational logic. Combinational logic only has and or not gates, only implements Boolean functions. Okay? All right, so only if one of the signals in its sensitivity list changes is the process triggered and this code evaluated, right? That implies that for a combinational process, we have to include all of the signals that appear on the right-hand side of an assignment within the process in the sensitivity list, because we know that when any one of those signals changes, potentially the output or the signal that we're assigning it to is going to change as well, right? So we have to include W0 and W1 in this case, but the other important type of signal that has to be included is if there's a conditional statement in here that involves a signal, we also have to include those signals in our sensitivity list, because it may change the order or change the behavior, change the assignment that should normally be made. If S is initially 1, for example, we would have assigned W1 to F, but when S changes to 0, then it should be W0 that gets assigned to F, right? Because that's what a mux does. It responds immediately when the select signal changes and changes which input it is that's routed through to the output. So we have to include not just any signal that appears on the right-hand side of an assignment, we also have to include all signals that appear in a conditional statement in the sensitivity list. And in doing so, this process is going to be triggered whenever there's a possible change in the output, right? Okay, good. We don't want to include any other spurious signals because it's unnecessary, certainly at this stage. So there's no point in adding D because D doesn't appear anywhere else anyway. And even if D did appear there, it doesn't necessarily make sense to trigger this process if there's a change in D, given that D has no impact on the output F, right? Okay, good. Right, we're going to look at some of the other implications of this in the following half a dozen slides or so. So here's another way of expressing the same code. We make an assignment of W0 to F, and because of the sequential evaluation, we check whether S is 1, and if it is, we actually assign W1 to F. Right? So there's a default assignment of W0 to F, but if S happens to be 1, then W1 is the value that gets assigned to F. All right? So I've got a couple of questions for you. Think about just a little. What would be the behavior of the process if this first assignment were moved to below the if statement? Yes?
It would always be assigned to W0?
Yes. F would always be W0 then, right? Because it's always going to be executed and it's the last assignment that's made to F. So that's clear. What about this second point? What if the first assignment were removed altogether. What then? Yeah.
F would be undefined if S was 0, and then only if S was 1, then it would stay W1 and it would never change after that.
Okay. I think you're on the right you're on the right track. I think I'd like to hear a clearer explanation of what might happen though. If we deleted this assignment of W0 to F, then only when S is 1 do we have W1 assigned to F, right? So what should be assigned to F if S is not 1? Well, there's no assignment made, so it should stay the same, shouldn't it? So that implies we're going to have some memory that remembers what the present value of F is. Otherwise, we can't execute this properly. All right? Now, we'll get onto this soon, because that leads us to how you describe sequential components using VHDL. Before we do that, let's have a look at a few more slightly more complex, slightly more sophisticated expressions, perhaps slightly more valid uses of a process here to describe a priority encoder, right? So this was the encoder that takes a 4-bit vector as an input and encodes which is the leading one that's on within that vector, right? So the most significant one tells us what Y0, Y1 output should be. And Z is only 1 if there is a 1 in that input vector. Otherwise, it's 0. So for a start, one of the things that you can observe is we have this process here, and we also have a concurrent, well, a conditional signal assignment statement here to Z. Okay? So they're running concurrently. This logic, or the hardware that gets specified for Z, operates in parallel with the hardware specified by the process. So they're both concurrent. So process is just a complex concurrent statement. Can you imagine what this circuit looks like? Does anybody have an idea what that circuit looks like? Remember our code for the 2-to-1 mux? What did that look like? If S equals 0, assign to F W0, otherwise assign to F W1. What's different about this? Well, if it were a 4-input mux, what would the selectors be? There's 2 selectors for a 4-input mux. I think it's going to be rather a chain of muxes, isn't it? What have we got here? 11 being 1, 1 being one 0, isn't it? And this is W2. Right? Does that make sense? Right. something like that. You could optimize that potentially, but I think that's going to be fine. Here's another way of specifying the same design, slightly different, because this one makes potentially multiple assignments to y, right? But it's only the last one that's committed when we exit the process. And at that stage, we'll get an assignment to y as well as to z occurring. Yeah? All right, so here's the description of a 2-bit comparator, right, where we make a default assignment to a equal b of 0, and if a does equal b, whatever a and b are, they're just 1-bit standard logic signals, then 1 is assigned to a equal b. Can you visualize what sort of circuit is going to be generated for this code? How do we make this check of a equal to b? What's a 2-bit equality circuit? So you want that to be 1 when a and b are both 0 and 1 when a and b are both 1, right? But if a is 1 and b is 0, or a is 0 and b is 1, sorry?
No.
X nor, right? Okay, so we want this. That's what's being generated by this or specified by this. Is that a sensible circuit? Do we really need a process for this?
Yes.
Why?
As soon as either A or B changes, you have to reevaluate.
True. You've already got an XNOR gate there. Do you need the mux as well? Because when the XNOR is 0, you're assigning 0 to A equal B. And when the XNOR is 1, you're assigning 1 to A equal B. So you don't really need the mux, do you? You only need the XNOR gate. And if you only need the XNOR gate, do we really need a process? No. We just say A equal B is assigned A XNOR B, right? So please stay alert when you're designing. Do not use a process unless you really need to, because you're opening up a can of worms in terms of correctness. Right, what about this circuit? Well, that's exactly what we were talking about previously, where we don't have a default assignment to A equal B. So when A is not equal B, we have to remember what the current value of A equal B is. And one way of doing that is to recycle it so we have sort of a feedback loop there. And that's the beginnings of how sequential logic is implemented. All right? So this is saying when A equal B equals 0, we don't want to change, when the output of this XNOR gate is 0, we don't want to change the value of A equals B. But when the output of the XNOR gate is 1, we want to assign it a 1. And once it's become 1, it's going to stay 1 forever, right? Again, probably not a very good reason to have a process. But this is one of the hazards you need to be aware of with your use of processes, that you always need to make an assignment to every output within the process, irrespective of what execution path is taken through that process. If you don't, you're going to infer memory. You're going to infer the existence of some sort of memory to keep track of the current value, given it's not made an assignment. So, to cut a long story short, processes that describe combinational logic, circuits without memory, must assign a value to every output signal for every execution path. Otherwise, they'll infer memory. Okay, so please be very careful of this. We'll exploit that in the next lecture, as you will see, to create flip-flops. All right, case statement. This is also a way that we could specify 2 to 1 mux. Case S, here we have a signal. When it's 0, assign W0 to F. For anything else, assign W1 to F. W1, W0 on the right-hand side of assignment, so they have to be in the sensitivity list. S is a conditional signal, so it has to appear in the sensitivity list. Otherwise, this is not going to be combinational. If we drop any one of these out, that means the process is potentially not triggered when there should be a change in value to F. And as a consequence, it's not combinational anymore. It's not a direct relationship between inputs and outputs. Okay, here's an encoder. So taking a 2-bit signal W as an input and providing the output. What sort of circuit would implement this? So if this was a 2 to 1 mux, what's this? I don't think you're counting right. Any ideas? There's 4 possible conditions there, aren't there? So it must be a 4 to 1 mux. So it should look something like, so this is W, 1 down to 0. These are all 4-bit signals now, where we have, what is it, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. They're the 4 possibilities coming out. That's a 4-bit signal. And this goes into another mux, but this is a 2 to 1 mux, which has 0, 0, 0, 0 coming in based on the enable. This is the output Y, right? So that's what you would expect is being specified there or being generated, something like this. This is getting very similar to what you would have been doing, except I haven't allowed you to use a process to specify the LED values, right? But you could easily describe the code converter that you're implementing here, BCD to LED code converter, by simply describing what the output should be for each one of these cases. And note the others down here, that's a don't care. So you're leaving it up to the tool to decide what's the easiest way of implementing this, right? If you think of this as a big mux, though, you know, you'd have to have 7-bit outputs, and they'd be 16 to 1 muxes that you're generating here, right? 7 of them in parallel, effectively. Is that good? All right, we'll do one more, I think, and then we'll change tack a little. This is a nice example as well. This describes the behavior of a 4-bit ALU. So probably about 1970s, I'd say, this design came out. So what's that, 50 years, 55 years? It's a 55-year-old design for a 4-bit ALU. We've come a fair way. Now we're doing sort of 64-bit ALUs or much more sophisticated than this. But look at the description. Here it is. We've got S is a 3-bit selector, it's an input. A and B are both 4-input signals, and F is a 4-bit output, right? That's the behavior of the ALU here that's described. And this is how you would code that, or could code that in VHDL, code it behaviorally, right? We're saying this is an unsigned design, so B minus A and A minus B, they're both going to be unsigned. You know, if S is, S2 is 0, S1 is 1, and S0 is 1, then we're doing an addition of A and B. But if S2 is 1 and the other bits are 0, then we're doing the bitwise exclusive OR of these two words, and so on. So I have a question for you. Can you sort of imagine how the bit slice of this design would be described? Or what sort of circuit you would have resulting as the bit slice of this circuit? And by bit slice I mean, or stage I mean, effectively we've got 4-bit arguments and a 4-bit result. So for every bit we're going to be repeating the same design effectively. We have here a 3-bit selector. We've got 8 different assignments. So that should suggest we're going to have an 8-to-1 mux somewhere there, right? As a start. So let's just elaborate that a little. I'm going to draw it sideways. So this is S2 to 0 coming in. Right, so this is 0 here and 7 up the top, for example. So for 0, for the bit slice, so this is just producing 1 bit as an output. So this is Fi. So when the selectors are 0, I want a 0 bit coming out. So I just have 0 as the input. And when S is 1, 1, 1, I want to have a 1. So what should go into 6 as the input? No. This table tells you what, or this code tells you what the 6th input should be. It's just the AND of AI and BI, right? So what about the 5th input? Yeah. And the 4th? Yeah, okay. So here we're going to have an OR gate. Here we're going to have an exclusive OR gate, right? With AI and BI as the 2 inputs. Now, what about the 3 mathematical functions? So what did we do last week in talking about adding 2 numbers together? At every stage we used what? How was our ripple carry adder built? Yes. So for the ith bit, how did we add them together? What did we use? We had a full adder, exactly. So can we just share the one full adder amongst those 3 bits? I'm assuming there's some sort of carry in and there's some sort of carry out, and there's an FI output bit, but we have to be a bit tricky, because when the selectors are 0, 0, 1, we want to do B minus A. When the selectors are 0, 1, 0, we want to do A minus B. And when they're 0, 1, 1, we want to do A plus B. So how can we share the one full adder logic and yet do those three different calculations? Where the selectors determine what calculation we're going to be doing. That's a great idea, isn't it? Yeah. So if we're thinking about the left-hand operand, remember that in the full adder, in the ripple carry adder, we used an exclusive OR gate to do a subtraction, remember? Right. So for the other operand, which is a bit more straightforward, what should so if this is 0, 1, the select bit should be what? If we're going to share this amongst these three possibilities, what should that select bit be? So when we have 0, 0, 1, we have B minus A. When we have 0, 1, 0, we have A minus B. And when we have 0, 1, 1, we have A plus B. S, which? When you say the second bit, which one are you referring to?
For
S0? Which one?
sorry,
S1, very good. S1, okay. And what should the input be for when S1 is 0? Should be BI, right. Good. And when it's 1, we want AI. Right? So there's a little bit of unknown about what we've got to do here now. It's a little bit trickier. We could do the same thing as we've done here and use a mux to determine which argument it is in any case, right? So up here, let's draw a mux. And again, this is driven by S1, but now we want to flip these around. So this should be AI and BI, right? The problem is that when we have 0, 0, 1, we want to do a subtraction. When we have 0, 1, 0, we want to do a subtraction. And when we have 0, 1, 1, we want to do an addition. So there's we want to invert, form the ones complement of whichever one of these is selected when we have 0, 0, 1 or 0, 1, 0. But when we have 0, 1, 1, we want to do an addition. So I think the simplest solution is to put an exclusive OR gate in there, have this output come straight down, and the other input to that exclusive OR, remember that we used this technique in the ripple carry adder. It was a conditional inverter. When the other bit is 0, if this bit here is 0, then the other bit just goes straight through, because 0 and 0 is 0. Sorry, 0 exclusive OR 0 is 0, and 0 exclusive OR 1 is 1, right? But if this guy is 1, then it complements the other bit, because 1 and 0 is 1 as the output, 1 exclusive OR 0 is 1 as the output, and 1 exclusive OR 1 is 0 as the output. So this other bit that comes in is a conditional inverter. What should that be? Well, it's only got to be inverted when what have we got here? We want it inverted when we have 0, 0, 1 or 0, 1, 0. So when it's 1, 1, we want it adding. So the way I would draw that is make this a NAND and make this S0 and S1. Does that make sense? So now S0 and S1 control when the output of this mux is inverted and thereby determine when we're going to get a subtraction going on in this full adder rather than an addition. So now this output can just be shared amongst these three inputs here. Let me call this SI and call this SI. SI is probably not a good name because we've got those select bits. I'll call it OI. Right? Okay. I'll take up a couple more minutes and then we'll have a break. I think it's also interesting to have a look at, why am I not able to, to have a look at, if you go to the lectures, the week 3 lectures have the data sheet for the 74381 4-bit ALU. If you zoom into this a bit, you'll sort of see a few things that you should be able to understand now. Let's just do this a bit bigger. Have a look at the design here. We have A0, A1, A2, A3 up the top there, as is B0, B1, B2, B3, right? Here's S0, S1, and S2. The Cn is the carry into this block. Notice that there's a G and P over here that are active low. So there's a group generate and propagate that's created for this chip with the intention that you actually put a carry look-ahead circuit. You use this together with a carry look-ahead circuit to generate higher level carries, as in this design here. So here's 1, 2, 3, 4 copies of that circuit to make a 16-bit ALU, right? Here's a carry look-ahead circuit that takes those G's and P's to create the carries in between those blocks, just as we described in our lecture last week, right? So you should be able to appreciate that. Another thing I found interesting was, if you have a look at this logic circuit, back in these days, manufacturers weren't afraid to show their IP. That's changed quite a lot. Up the top here, we have A0 and B0. This is A0 and B1. This is A2 and B2 and A3 and B3 down the bottom. Here we have F0, F1, F2, and F3. Have a look at the circuit. What does that look like? What you're getting here. It's hard to see the full adder here, but notice how the complexity of this circuit is increasing. 2 gates, 3 gates, 4 gates. What does that remind you of? Also a carry look-ahead addition going on inside this chip, right, for the 4 bits. Yeah, that were the things that I thought were worth noting. Don't know that there's very much else that's useful at this point in time. Is there a date on it? Don't know how old this actually is. Can't see a date down there. Yeah, but it's much older than 1988, believe me. It's probably, like I say, early 70s. I'm not too sure when the, 74381 it might be if we go to Righto. Oh, it might even be older. It doesn't actually say there. All right. Believe me, it was around the 1970s, early 1970s, somewhere around then. All right, let's have a 5-minute break, and we'll shift gears a little when we come back. We'll talk about the Shannon expansion theorem, and then we'll be done for the day. Are there any questions? Okay. Let's just grab this. Right, is there anybody else coming back? Those people just leave? Oh no, there's somebody coming back there. All right, well, I think we can just quickly cover this slide off. It doesn't really tell us anything very important. It's more a reference slide than anything else, explaining the relative precedence of operators within VHDL. In this table, the top, like the precedence goes in bands of groups of operators from the top down to the bottom in terms of order. So the logical operators are the highest precedence, and or nan, nor, exclusive nor, and not. Within and though, they all have the same order of precedence, so you need to use parentheses to indicate what order you want things evaluated in, okay? I think that's all that's important at this stage. What I want to get onto is really the use of multiplexers to implement functions. And the first few slides here are really just a review of where we came from, what we'd already talked about. We saw how to implement the exclusive OR function using a 4-to-1 mux, whereby the two variables that we want to form the exclusive OR between become the select inputs of the mux. And we hardwire the inputs to the mux to 0, either voltage low or voltage high. We can be more efficient, we found out previously already, by using a 2-to-1 mux rather than a 4-to-1 mux, in which we use one of the variables, one of the input signals that's going to be determining what the function should be, as selector on a 2-to-1 mux. We notice that when W1 is 0, then the function output should just be the same as W2. But when W1 is 1, the function output should be the complement of W2. And so obviously this circuit that we see down below results from that. We also looked at the 3-input majority function using a 4-to-1 mux, using a similar concept here where we use 2 bits to select which function is going to be output here, and by simply combining the 2 rows respectively of the truth table for each possible combination of the inputs W1 and W2, we determined whether the output should be 0, 1, W3, or the complement of W3. This is the resulting circuit that we got. We could work on a number of other examples. Here's an example of how one could map a 3-bit exclusive OR function to 2 2-to-1 muxes. I'll leave it to you to think about it in detail a little bit more, but really W1 is determining whether we're in the top half of this truth table or the bottom half, whereby we have the first mux here computing the exclusive OR of W2 and W3, and that then is what gets routed out to F when W1 is 0, the exclusive OR of W2 and W3. Otherwise, it's the exclusive NOR, so the complement of W2 exclusive OR W3 that's routed through to the output F. The same function using a 4-to-1 mux uses 2 selectors, and then we're really literally just implementing 0, 1, or W3, or the complement of W3 here. So over a number of examples, what we can see is that we can implement arbitrary functions using zeros, ones, and some other variable or its complement to implement that function using a mux. But we can also choose to use more complex circuits as the inputs to the mux, using other Boolean functions like AND or a NOT. And so let's have a look at how that might work for the 3-input majority function. Here is the 3-input majority function. And in this case, if we were only using W1 as the selector for a 2-to-1 mux, then the first 4 lines look like the AND of W2 and W3, whereas the bottom 4 lines look like the OR of W2 and W3. So obviously this then is the resulting circuit that we would get if we wanted to target a 2-to-1 mux. We could also derive this algebraically by firstly just listing the canonical sum of product form. So for all of the ones there, listing the term, and then factorizing that around W1 if that's the selector that we want to use for our mux. And we then get the only term that has not W1 in it is the first one, so we're left with the residual of W2, W3, whereas the other 3 SOP terms all contain W1, so if we factorize out the W1, we're left with the residual, not W2, W3, etc., which of course can be simplified because we can combine W2, W3 with each one of these 2 terms in order to simplify it just down to W2 or W3. Okay, so that's the resulting function, and of course that's exactly what's implemented up here. So what we're going to do is formalize this derivation somewhat so that we can see always, without doing some sort of mental gymnastics as to what how the truth table might be simplified to arrive at a nice simple implementation. So in order to do that, we make use of Shannon's expansion theorem. And essentially that says that mux implementations of logic functions require that a given function be decomposed with respect to that variable that's going to be used as the select input. So more formally, we can say that any Boolean function of n variables can be written in the form W1, not W1, let's say, and the residual of all of those terms that involve W1 bar, or W1 and the residual of all of those terms that involve W1, which is what we did on the previous slide. And we'll look at this in a few more examples to see how that's done. We don't have to expand around W1. We could choose any one of the n variables to expand around, and effectively we're just replacing then that variable within all of the terms in order to determine what the residuals are. So here's a couple of examples. Let's have a look at this one first. So this one describes the 3-input majority function, right? This tells us when 2 or more bits in the input are asserted. So this is going to be one when we have W1 and W2, or W1 and W3, or W2 and W3. So that's just the simplified SOP form for a input majority function. Expanding around W1, the input W1, the only term that involves not W1 is this last one, because these other two terms involve W1. Okay? So only the last term is a residual when we take out W1 bar, whereas the residual of the other two terms when W1 is extracted is given, well, it's all three actually, because this one also contains W1. Remember, we can expand this as not W1, W2, W3, or W1, W2, W3, right? So having done that mentally, here's the not W1, W2, W3, and here's the W1, W2, W3. And we get the W2 and W3 from the other two terms that are here, and of course we can simplify this because W2 or W2, W3 is just W2 or W3, right? Okay, so that's the simplified form, this is the Shannon expansion when we expand around W1 for the 3-input majority function. Performing the same operation on the 3-input exclusive OR function looks like this. So this is the 3-input exclusive OR. Writing that out longhand, this is what that means. This means it's not W1 and the exclusive OR of W2 and W3, or it's W1 and the exclusive NOR of W2 and W3. And obviously we can see then that residual for W1 bar is just W2 exclusive OR W3, and the residual of W1 is just the exclusive OR of W2, W3, exclusive NOR thereof. Okay, so we call this residual, what's left over when we take out W1 bar, the cofactor of F. So that's just a shorthand notation for the residuals of all of those terms that involve W1 bar. Similarly, we call the term that is the residual of all of those terms that have W1, that contain W1, the cofactor of F with respect to W1. So we can write in shorthand the expansion in this way here. So we have F is equal to W1 bar and the cofactor of F with respect to W1 bar, or W1 and the cofactor of F with respect to W1. We can do that in general for any one of the n variables that are in our function. So for the ith one, we would write it this way. Okay, so why that's important is that depending upon the function, one of the expansions might be cheaper than all of the rest. And we obviously want to find the one that's the cheapest. Okay, and that requires a little bit of intuition. It's not necessarily straightforward or obvious which is the cheapest. So take this function as an example. F is not W1, W3, or W2 and W3 bar. In order to perform the expansion with respect to W1, it's probably easiest for you, when you haven't got the experience yet, to just expand this into its canonical form. And that means rewriting this as the 4 terms, taking the first term here and ANDing it with not W2, which is this first term, and ANDing it with W2, which is the second term. So we've just expanded that term into its canonical form. Similarly, for the latter term here, we have to expand it with not W1 or W1, which is these latter 2 terms, okay? Then we can perform our Shannon decomposition. In this case, let's do it with respect to W1. So the terms that have not W1 in it are the first one, the second one, and the third one, right? The fourth one has W1 in it. So we see that for not W1, its cofactor, the cofactor of F with respect to W1 bar is not W2, not W2 W3, or W2 W3, or W2 not W3, as we see listed here. That can be simplified, of course. And the cofactor of F with respect to W1 is simply W2 W3 bar, as we see here. So simplifying this guy, well, we can combine the first 2 terms to eliminate W2, that gives us W3. And we can combine the second 2 terms, the last 2 terms, sorry, to eliminate W3, which gives us W2. So this is the resulting function. We can perform the same decomposition with respect to W2. And when we do that, this is the expansion that results. And that has the same shape as this expansion, so it's not cheaper, right? And if we expand with respect to W3, it just so happens that W3 appears in uncomplemented and in complemented form in both terms, so the resulting residuals are W2 and not W1, and clearly that's cheaper than the other 2 implementations, right? Doesn't have an AND or an OR gate in it, right? This involves an AND gate and this involves an OR gate. Neither of those are required in this implementation. Yeah?
How do we decompose with not W1 in the first step?
Okay, so we're just factorizing out for all of those terms that have not W1 in it, factorizing out not W1. That gives us this line, okay? Sorry, this line here. Can you see that?
No,
So you can't see this?
like I can, but I don't understand how we got that from just the first line of the term.
Oh, because what we did was rewrite this in its canonical SOP form. So we expanded this expression. I think once you get used to it, you don't need to do that step. But initially, to understand how the decomposition is done, it's easier to first rewrite the expression in canonical form, because then it's clear which terms have to be combined. What's the cofactor of F with respect to W1 bar, and what's the cofactor with respect to W1?
Okay, I see what happened now.
Okay, good. So clearly here, decomposing with respect to W3 is cheapest. I missed the step in between, but we would have had, well, what are the functions with, what are the terms that can include W3 bar? It's only the latter 2, W1 bar, W2, and W1, W2. And clearly we can eliminate W1 from those 2 and only be left with W2, which is what we've got here. Similarly, for the cofactor with respect to W3, it's only the first 2 terms that include W3. We have not W1, not W2, or not W1, W2 as the cofactor, whereby we can eliminate W2 and be left with just W1 bar. Okay? But we could have gone here just by inspection. We can see that both terms have W3 either in uncomplemented or complemented form, and so we can write down the cofactors straight by inspection. Okay, we don't just have to expand with respect to one variable. We could be doing it with multiple variables. So if we're mapping to a 4-to-1 mux, then we want to do our Shannon expansion with respect to 2 variables, because we've got 2 selectors on a 4-to-1 mux. Here is the expansion with respect to W1 and W2, right? So now we have 4 cofactors that we need to find. And we can keep on going. If we expand with respect to all n variables, then we've got effectively an n-input lookup table implementation where we've simply got the canonical form that leads to the final result. And we'll have a look at what that looks like. Right, so let's have a look at another example here. Here we have f is equal to W1 bar and W3 bar, or W1, W2, or W1, W3. And we want to implement it using a 2-to-1 mux. So if we expand around W1, we'll see that, well, only the first term has W1 bar, so W3 bar is the residual, and there's the latter 2 terms that have W1 in it, so we have W2 or W3 as being the residual there. Is that clear? Okay, good. So that's the resulting circuit. If we expanded around W2, this would be the result. That's clearly more expensive than this. And if we expand around W3, this would be the result. That's going to be roughly the same cost as this guy, right? So neither of those are cheaper than this expansion. If you were to use a 4-to-1 mux, you could decompose with respect to W1 and W2. So what does that look like then? Well, to do it in our head, what are the terms here that involve W1 bar and W2 bar? Well, the first one, because that involves W1 bar, W2 bar, W3 bar, or W1 bar, W2, W3 bar. The other 2 terms only have W1, so neither of those can be involved. So it's only W3 bar that's the residual, which is what we've got here. The next one to consider is W1 bar, W2. What terms have W1 bar, W2 in them? Well, again, it's only the first term here. So again, W3 is the residual for that, W3 bar, sorry. Then for W1, W2 bar, we could have that last term. So that's going to have W3 as the residual. And for W1, W2, it's only the middle term. And of course, when we take W1, W2 out, we're left with 1. So 1 is the residual. Is that clear? Probably a bit of a jump from going from 1 variable to expanding around 2, but it's the same principle. So if you write out the canonical SOP form, it's very easy to derive these 3, these 4. Are you right? Or do you need me to do that? Good. Any other concerns there? All clear? Not 100% sure? You okay? Yeah? All right. Good, good. Right. Okay, so here's a function which has 3 variables. If we wanted to use an 8-to-1 mux, do you know what the driving functions are going to be? They're only going to be 0 or 1. Because if we expand this into its canonical SOP form, all of the 8 combinations, not W1, not W2, not W3, are going to have a residual of 1 or 0. It's either going to be in the function or not going to be in the function, right? This expands to not W1, not W2, not W3. It also expands to W1 bar, W2, W3 bar. So obviously the first minterm 0 and minterm 2 are covered there. This guy covers minterms, what is it, W1, W2, not W3, which is minterm 6, and W1, W2, W3, which is minterm 7. So 6 and 7 are going to have a 1 associated with them. And this guy has W1, not W2, W3, which is minterm 5, W1, W2, W3, which is minterm 7 again, right? So this is our expansion, and this is what it looks like. Minterm 0, minterm 2, minterm 5, 6, and 7, as we identified, are going to have the 1s with it. No other minterm appears in the canonical sum of products, therefore they're all 0s, and this is what the implementation looks like. We have our 3 variables driving the input, they're the selectors, and we're either associating a 0 or a 1 with each one of those minterms. And you can think of this as being the program of the 3 input lookup table that determines that function. Any question on this? So all we're doing is saying that when we expand with respect to all variables, what we get is an n to 1, a 2 to the n to 1 mux, here an 8 to 1 mux for 3 variables. And each input of the mux is going to be driven with either a 0 or a 1, because either that minterm is included in the function or it's not included in the function. Okay, now we've got another 6, 7, 8 minutes to go. I think I'll get through these, but it'll be pretty quick. I'm going to keep up the pace that we've been going at. Any 4-input function can be mapped to at most 3 input lookup tables, which would look like this, structured in this way. For example, consider this function, which has 4 variables, W1 through W4. If we expand around W1, this is the expansion that we get from these inputs here. I'm not going to go into the detail right now, but you can easily derive that from the canonical or read it off the function directly. We can apply absorption to these 2 terms because they have W2, W3 bar in common. So what's that? That's X or X, Y, which means it's X or Y. So we have therefore, this is the same as X or XY, where Y is W4. So that's the same as just X. X always has to be true for that to be true, X being W2, W3 bar. So in that case, what that means is to map it to 3 input lookup tables, we would map the cofactor of F with respect to W1 bar, just W2 and W3, because that only involves W2 and W3. This term drops away into one 3-LUT. And into the other 3-LUT, we need to have W2, W3, and W4 coming in. We can't simplify that any further. And we have W1 then selecting between those 2 in the 3rd 3-input lookup table. How would that lookup table be programmed? Well, this is a 3-input lookup table. So they're just addresses that I've put there. What function would the top one have to be? Well, it's got to implement this function here, W2 bar W3 or W2 W3 bar, right? W2 bar W3, W2 W3 bar, because we don't care about the other input. Right, it's just the exclusive OR of W2 and W3, right? And what's the other lookup table? What is it going to look like? Well, it's going to have not W2, W3. So 0, 1, 2, 3, 4, 5, 6, 7. Not W2, W3. So that's this guy here is 1. So we have 0, 1. And we have not W2, W3, a 1 down here at 5. We have W2, not W3, W4. So that's 5 as well. Did I do that wrong? This has got to be W2, not W2. It should have been 1, 1 here because this is W2, 3, 4. So 2 and 3 is 1, and then we have 5 being 1. Yep. And finally we have not W2, not W4. So we have a 1 here. A 1 in 2, a 1 in, it's only those two, and the rest is right. So this is F of W1 bar, this is F of W1, and this comes into a lookup table which has W1 coming in here as well, being the most significant bit. All I'm doing here is showing you how these lookup tables are programmed effectively. So when W1 is 0, we just want FW1 bar to be the output. So whatever this value is, so this is W1, FW1 bar, and finally FW1 being the last bit, let's say. So we would have 0, 0, 1, 1. When W1 is 0, and when W1 is 1, what we want is FW1, so we want 0, 1, 0, 1 as the program output for our function f. It's not really important. I probably wouldn't ask you to do too many programming questions, but this just shows how you could derive what those programs would be just from these expressions. I think it's just worth finishing this slide off. If we used W2 instead of W1, then this would be the expression that we get. And this is a simpler circuit. It looks just like this. We only need 2 3-input lookup tables then. Why? Because it happens that this residual, this cofactor of f with respect to W2 is the complement of the cofactor of f with respect to W2 bar. Because we can factorize this with W3 bar, and that's outside of W1 bar or W4, and this is clearly just by De Morgan the complement of this expression. Because we complement W3, the OR becomes an AND, this becomes an OR, and these two terms are complemented. So clearly they're complements of each other, and therefore we can get away with the 1. What would be the program of this guy if we were using that second implementation? Well, let's do both of them quickly. So this is taking W1, W3, and W4. So this is W1, W3, W4. And we're implementing, we're going to implement the complement. So F, the cofactor of F with respect to W2 bar, which is this. So it's going to be asserted whenever W3 is asserted, which are in those two, or when we have W1 not W4, which is here and here. And in every other case, that's 0, and that's going to come into this other lookup table, which has W2 coming in as well. So this is F, and we have 0. So we have right, and this is saying, well, when W2 is 0, we want this value. So when W2 is 0, that's in the first two rows, and that means we're just copying whatever f, the cofactor of f with respect to W2 bar. So it's 0 and 1 in the first 2 bit positions. Down here, when W2 is 0, it's got to be 0, 1 as well. And when W1 is 1, we want the complement of this. So when W1 is 1 and the input is 0, we want to output a 1. And when the input's 1, we want to output a 0. Same here. So that's what the program should look like. It's just the exclusive NOR of those 3 bits. Okay, sorry for keeping you. Sorry, I got a bit carried away today. You've seen me in full flight. Sorry about that. So you've got 4 minutes to get to your next lecture if you've got another one. Any questions? Is this clear, or have I completely wasted everybody's time? Did this make sense?
Yes, but I feel like we would need to do it ourselves.
Yeah. There may be 1 or 2 questions that would be simpler than these problems, I think, based on that would ask you, what would the lookup table be programmed like for this function? You know, be more along the lines of how would you implement exclusive OR on a 2-to-1 lookup table, I'd say, which should be pretty straightforward. All right, any questions on the other stuff? We've still got a couple of slides to go, but we're pretty much at the end of the lecture. You all look like you need to go home. Need to have a beer. Right, I'll leave you to it. Have a good weekend. See you on Tuesday. No worries.
Thank you.
You're welcome.
So if you want to find the canonical form, it's basically just any like
Expanding so that you've got all n variables in there.
yeah,
And expanding every term.
yeah. So if you're like missing a variable in one term, you just do the fact that 1 equals a complement plus a non-complement. Okay.
That's right. You've got to end it then with 1, which is equal to x or x bar.
Yeah.
Yeah.
Awesome.
Yeah, that's it.
See you next week.
See ya. Bye. See you.